What if the Big Bang was not the first moment of existence, but only the point where our cosmic history becomes visible? The universe was once hotter, denser, and more extreme than anything seen today. Yet when physics follows that history backward toward the Planck scale, the familiar equations begin to lose their certainty. Beyond that boundary may lie inflation, a quantum bounce, an earlier cosmic cycle, or perhaps a realm where time itself has not yet taken its familiar form. If calm journeys into questions like these belong in your quiet hours, liking, subscribing, and sharing helps Calm Space Science continue creating them. Thank you for choosing to spend part of your time here. And if you feel like joining the community, leave a comment with the city or country you are listening from, what time it is there, and whether this finds you studying, relaxing, or preparing for sleep. From here, the path leads backward not toward certainty, but toward the deepest edge of what physics can presently describe. The phrase Big Bang carries an image that is difficult to remove. It suggests a detonation, a sudden burst of matter from a single point, perhaps into an empty darkness that had been waiting around it. That image is memorable, but it is also misleading. The modern cosmological idea is not that a bomb exploded somewhere in space. It is that space itself was once in a much hotter, denser state, and that the distances between widely separated regions have been increasing as the universe evolves. Galaxies are not simply flying away from a central blast site through a fixed background. On the largest scales, the geometry of the universe changes with time, so that the space between distant structures grows. Reversing that history leads toward an earlier cosmos in which matter and radiation were packed far more closely together. Temperatures were vastly higher, and the forms of structure familiar today had not yet appeared. This is the core of the hot Big Bang model, and it is one of the most successful frameworks in modern science. It explains why the universe expands, why a faint thermal afterglow fills the sky, why the earliest chemical elements exist in the proportions they do, and why cosmic structure grows from small initial irregularities into galaxies and clusters. None of this requires the claim that the universe emerged from absolute nothingness. That is a separate statement, and it reaches beyond what the hot Big Bang model by itself establishes. The distinction matters because the word beginning can hide several different ideas inside a single familiar phrase. There can be a beginning of the hot, dense phase that eventually produces the observable universe. There can be a beginning of the period described reliably by current theories. There can be a beginning of cosmic expansion as it is usually modelled, and there can be an absolute beginning of time itself, before which no earlier state, process, or duration exists. These are not automatically the same boundary. The hot Big Bang concerns the first of them most directly. It describes a thermal history. At very early times, the universe is filled with an intense mixture of radiation and elementary particles. As expansion proceeds, the temperature falls. Particles combine into more stable forms. Atomic nuclei appear. Much later, electrons settle into atoms, allowing light to travel more freely, over still greater spans. Gravity amplifies slight differences in density, and large-scale structure emerges. The model therefore begins not with a picture of creation from nothing, but with a physical state and an evolution away from it. The farther backward the equations are followed, however, the more extreme the conditions become. Density rises, temperature rises, curvature can rise. Eventually, the assumptions used in ordinary descriptions become strained, and this is where the language of origins becomes dangerous if it is treated too casually. A theory can successfully describe how a system behaves over a wide range of conditions while failing near a boundary where new physics becomes important. The failure of the theory at that boundary does not automatically reveal what reality itself does there. Classical general relativity provides the clearest example. It describes gravity not as a conventional force acting through space, but as the geometry of spacetime. Matter and energy influence that geometry, and the geometry in turn influences motion, applied to a universe that is expanding today. General relativity naturally permits solutions in which the scale of the cosmos was smaller in the past. Under broad conditions, those solutions can be driven toward a state in which the classical description becomes singular. Quantities that normally remain finite can cease to behave well in the mathematics. It is tempting to call that singularity the first instant and stop the story there. Yet that interpretation quietly assumes that the classical theory remains physically trustworthy precisely where its own equations are signaling a breakdown. Cosmology, therefore, contains a subtle divide between what is observed, what is inferred within established theory, and what is projected beyond the theory's tested domain. The hot and dense early universe sits on the well-supported side of that divide. An absolute origin of time does not. Even the phrase before the Big Bang can mean different things depending on which version of the Big Bang is intended. If Big Bang refers to the hot expanding phase after an earlier period such as cosmic inflation, then asking what came before is scientifically meaningful within many models. If Big Bang refers instead to a classical singular boundary, the question becomes more difficult, because ordinary time itself may not extend through that boundary in the way familiar intuition expects. And if some future theory replaces the singularity with a bounce, a quantum transition, or an emergent phase, then the same phrase would point to an earlier physical history rather than an impossible question. The uncertainty is not a weakness in the evidence for the hot Big Bang. It reflects the fact that a model can be extremely well confirmed over one range while leaving another range open. The expansion history of the universe can be measured. The cosmic microwave background can be mapped. The abundances of light elements can be compared with calculations from the early thermal universe. None of those observations reaches an absolute first moment. They reach back toward an era when the universe was young, hot, smooth, and dense, but they do not provide a direct view of an ultimate temporal edge. This is why modern cosmology can be confident about much of early cosmic history while remaining cautious about the word beginning. The confidence and the caution belong together. They concern different layers of the problem. The same distinction also prevents a common misunderstanding about the location of the Big Bang. If cosmic expansion is a stretching of space itself, then there is no ordinary central point from which all galaxies are moving away. Every sufficiently distant region sees other distant regions receding in a pattern described by the large-scale expansion. The early hot state was not confined to one place inside a larger empty arena. It characterized the observable universe everywhere. In that sense, the Big Bang happened not at a special location but throughout the region that later became the cosmos now visible. This does not mean that every local object expands with the universe. Galaxies, solar systems, planets, and atoms can remain bound because local forces overwhelm the extremely gentle effect of cosmic expansion on those scales. But on immense distances, the changing geometry becomes the dominant pattern, and tracing that pattern backward leads to the ancient thermal state from which the familiar universe develops. That picture already carries enough strangeness without adding claims that the evidence does not require. Space does not need an external room into which it expands. The universe does not need a center in the ordinary sense. The hot Big Bang does not need to be an explosion, and the earliest state that current cosmology can describe does not need to be the absolute first state that ever existed. Once those distinctions are kept separate, the origin problem becomes both narrower and deeper. The question is no longer whether the Big Bang happened in the scientific sense supported by observation. The stronger question is, what kind of boundary lies behind the hot early universe? It may be a point where classical equations fail. It may be the end of an earlier inflationary phase. It may conceal a regime in which quantum gravity changes the meaning of space-time. It may eventually be replaced by a model with no singular beginning at all. None of these possibilities is established simply by recognizing the hot Big Bang, and none can erase the observational success of the thermal history that follows. The result is a more careful picture of cosmic origins. The universe has a well-supported early chapter in which it is hotter, denser, and smoother than it is now. That chapter can be traced backward with impressive precision for a long distance, but the word beginning lies beyond the safest part of that reconstruction. The Big Bang marks the doorway into the history that current cosmology understands best. Whether that doorway is also the first threshold of time remains a separate question, and answering it requires physics that reaches deeper than the hot Big Bang itself. The strength of the hot Big Bang model does not come from a single dramatic observation. It comes from several independent lines of evidence that converge on the same history the universe was once hotter, denser, smoother, and far less chemically developed than it is now. The first of these clues is expansion. On sufficiently large scales, Distant galaxies show a systematic recession whose speed increases with distance. This pattern is not interpreted as ordinary motion through a fixed cosmic stage, but as the growth of distances within an expanding spacetime. When the expansion is mathematically reversed, the average separation between large structures decreases, and the energy contained in matter and radiation is forced into a smaller volume. That simple reversal already points toward an earlier universe with higher density. But expansion alone would not be enough. A wide range of cosmic histories might include expansion, and so the deeper case depends on whether other observations carry the same thermal memory. The most important of these is the cosmic microwave background, a nearly uniform bath of radiation arriving from every direction in the sky. It is extraordinarily cold today, only a few degrees above absolute zero, but its spectrum has the precise shape expected of thermal radiation that has been stretched and cooled by cosmic expansion. This radiation is not light from the first instant. It comes from a later stage, hundreds of thousands of years after the hot early universe began evolving, when the expanding cosmos had cooled enough for electrons to combine with atomic nuclei and form neutral atoms. Before that transition, free electrons scattered photons repeatedly, making the universe opaque in much the same way that light is scattered inside a dense fog. Once neutral atoms formed, photons could travel far more freely. The radiation released from that transition has continued across space ever since, losing energy as the universe expands and becoming the microwave background measured today. Its existence was predicted before it was observed, and its properties became one of the clearest demonstrations that the early universe really did pass through a hot thermal phase. The background is not perfectly uniform. Tiny temperature differences appear across the sky, variations so small that their importance only becomes clear when gravity is allowed time to act. Those slight irregularities correspond to early differences in density. Regions that begin marginally denser can attract more matter, and over immense spans they become the seeds from which galaxies, clusters, and the large cosmic web eventually grow. This creates a remarkable connection between the smooth radiation of the young universe and the highly structured cosmos seen much later. The same model that explains why the microwave background exists also explains why it contains a pattern of small fluctuations rather than perfect sameness. Their statistical structure carries information about the composition, geometry, and early dynamics of the universe, and those measurements have repeatedly strengthened the broader hot Big Bang picture. A third line of evidence comes from chemistry. The earliest universe was too hot for atomic nuclei to remain intact. As expansion lowered the temperature, protons and neutrons could begin combining into simple nuclei during a brief period of primordial nucleosynthesis. The conditions did not persist long enough to build the rich periodic table found in stars and planets today. Instead, the process favored the lightest nuclei, especially hydrogen and helium, with smaller amounts of deuterium and other light species. The predicted proportions depend on the physical conditions of the young universe, including its density and rate of expansion. Observations broadly match the pattern expected from this early nuclear furnace. Heavier elements such as carbon, oxygen, plamero, silicon, and iron require later astrophysical environments, especially stars and stellar explosions. But much of the hydrogen and helium that fills the cosmos carries a far older origin. In that sense, the ordinary matter in galaxies still preserves a chemical signature from the first minutes of the hot expanding phase. Expansion, relic radiation, and primordial element formation therefore reinforce one another. Each involves a different kind of physics and a different kind of observation. Their agreement would be difficult to explain as an accident. Large-scale structure adds another layer. Galaxies are not scattered randomly. They form filaments, sheets, clusters, and immense low-density voids. The distribution seen today is consistent with gravitational growth from much smaller density variations in the early universe, including the variations recorded in the microwave background. The mature cosmic web and the faint temperature pattern in ancient radiation are separated by billions of years, yet they can be understood as different stages of the same evolving system. This continuity gives the hot Big Bang model its unusual strength. It does not merely fit one snapshot, it links states of the universe across time. The evidence is therefore cumulative. Cosmic expansion says that the universe was more compact in the past, The microwave background says that it was once filled with hot radiation in near thermal equilibrium. Primordial abundances show that early temperatures and densities allowed specific nuclear reactions before the universe cooled too much for them to continue. Large-scale structure shows that small early irregularities could grow into the architecture observed today. Together, these observations define a coherent history extending deep into the past. Yet the reach of that history has a limit, and that limit matters for the question of whether time itself began. None of these observations directly records an absolute first instant. The microwave background comes from long after the earliest regimes under discussion. Primordial nucleosynthesis reaches further back, but still takes place after the universe has already entered an expanding hot phase. Measurements of galaxies and large-scale structure concern later consequences of earlier conditions. Even the inference of expansion, when reversed, tells how the universe behaves within a model. It does not by itself reveal whether the model remains valid without modification at arbitrarily high density. The distinction resembles the difference between reconstructing a river upstream and proving where the first molecule of water entered the system. A long section of the course may be mapped with confidence, even if the ultimate source lies behind terrain that has not yet been reached. In cosmology, the unknown terrain begins where temperatures and energies become so extreme that the established theories can no longer be trusted in the same way. That is why the phrase evidence for the Big Bang must be used carefully. There is overwhelming evidence for a hot, dense early universe and for its subsequent expansion and cooling. There is not equivalent observational evidence for creation from nothing, for a literal point of infinite density, or for the claim that no physical description can extend to an earlier regime. Those possibilities belong to a different layer of reasoning. Some emerge from extrapolating classical general relativity backward. Others arise from proposed quantum theories of gravity or from alternative cosmological models. But the observational pillars themselves remain more modest and more secure. They tell a story of thermal history, not necessarily of metaphysical origin. This is also why alternative ideas about a pre-Big Bang phase do not automatically compete with the evidence that established the hot Big Bang. A model containing a bounce, an earlier contraction, or some quantum boundary would still need to produce the same successful hot expanding phase afterward. It would have to preserve the conditions required for primordial nucleosynthesis, the origin and structure of the microwave background, and the later formation of galaxies and clusters. Any deeper theory must therefore inherit the observational achievements of the standard account rather than discard them. The question is not whether the young universe was hot and dense. The question is what, if anything, lies behind that condition. The evidence narrows the possibilities because any successful deeper history must flow into the universe already reconstructed with considerable precision. At the same time, it leaves room at the earliest edge because the observations become indirect and the theoretical uncertainties grow. The farther backward the history is traced, the less it resembles a sequence of visible events and the more it becomes a test of how far known physical laws can be extended. The hot Big Bang is therefore both a triumph and a boundary marker. It gives cosmology a firm account of an early thermal universe, but it does not close the question of origins. Instead, its success makes the unresolved problem sharper. If the evidence so clearly points toward a hotter and denser past, then the next step is to ask what happens when that trend is continued backward toward conditions where density, temperature, and curvature become extreme. That is where the observational story hands the problem to the equations, and where the path toward the beginning becomes increasingly difficult to follow. Rewinding the universe does not require imagining galaxies literally racing backward through space toward a single point. The more precise picture begins with the expansion itself. On large scales, the average distance between widely separated regions changes with cosmic time, and the mathematical quantity used to track that change is called the scale factor. As the universe expands, the scale factor grows. Following the same equations into the past means allowing it to shrink, so that a given amount of matter and radiation occupies a smaller cosmic volume. The consequences appear quickly. Matter becomes more concentrated. Radiation becomes more energetic. Typical wavelengths shorten. Temperatures rise. Processes that are impossible in the cool modern universe become unavoidable, because particles collide more frequently and with greater energy. The familiar arrangement of galaxies, stars, atoms, and nuclei does not survive indefinitely under that reversal. Each layer of structure disappears as the conditions required to hold it together are exceeded, long before stars can exist. Matter is distributed through a much smoother cosmos. Earlier still, neutral atoms cannot remain intact because energetic radiation repeatedly ionizes them. Farther back, even atomic nuclei are subjected to temperatures high enough that only the simplest nuclear reactions can proceed for long. Reversing cosmic history therefore does not simply make the universe smaller, it changes the physical state of everything within it. Radiation is especially important in this reconstruction. Expansion stretches light, reducing the energy carried by individual photons and lowering the temperature of a thermal radiation field. Running the process backward compresses those wavelengths and raises their energy. The cosmic microwave background, cold today, is therefore understood as the cooled remnant of radiation that was once much hotter. This is not an optional detail added to the expansion picture. It is exactly the behavior expected when radiation propagates through an evolving spacetime. The same reasoning applies to matter density. In an expanding region, the same number of non-relativistic particles becomes spread over a larger volume. So average density falls. In the reverse direction, density rises. Radiation density rises even faster because compression increases both the number of photons per volume and the energy carried by each photon. At sufficiently early times, radiation dominates the cosmic energy budget, and the universe behaves very differently from the matter-dominated conditions that later allow galaxies and clusters to grow. The farther backward the calculation goes, the more the history becomes a sequence of transitions between physical regimes. There is no need for a sudden discontinuity to make the early universe strange. Ordinary expansion alone, reversed in time, is enough to remove one familiar structure after another. Galaxies cease to be meaningful as distinct systems. Stars vanish from the description because there has not yet been time for them to form. Atoms give way to a plasma of charged particles. Nuclei become unstable at still higher temperatures. Eventually, the description approaches energies at which the particle physics of the early universe itself becomes increasingly uncertain. This ladder of earlier conditions is one reason the hot Big Bang model is so powerful. Each stage leaves traces in the later cosmos. Those traces can be compared with observation. Yet the same ladder also shows why the deepest past becomes progressively harder to reconstruct. The farther back the equations are extended, the more extreme the inferred conditions become, and the less directly they can be tested. General relativity provides the framework that links this changing density to the geometry of spacetime. In a homogeneous and isotropic universe, the theory connects the expansion rate to the amount and type of energy present. When density increases toward the past, the curvature and dynamical behavior of spacetime can become more extreme as well. This does not mean that space is bending into some higher dimensional container. Curvature here is an intrinsic property of spacetime, expressed through how distances, duration, and trajectories behave within the universe itself. Under ordinary cosmic conditions, general relativity handles this relationship extraordinarily well. It explains the motion of planets, the dynamics of compact objects, gravitational lensing, gravitational waves, and the large-scale evolution of the cosmos. But success at accessible scales does not guarantee that the same classical description remains complete when density and curvature are pushed without limit. The backward extrapolation eventually drives the model toward precisely that problem. In the simplest classical solutions, the scale factor tends towards zero at a finite time in the past. Matter density rises without bound. Radiation density rises without bound. Curvature quantities can also diverge. The equations are no longer describing merely a very hot universe. They are approaching a boundary where the mathematical description itself becomes pathological. It is easy to mistake this outcome for a photograph of the first moment, as though general relativity has shown the universe compressed into a literal point and thereby identified the creation of time. What it actually shows is more cautious. If the classical equations are extended backward without modification, they encounter a singular limit. That statement is mathematically powerful, but its physical interpretation is not automatic. The difficulty can be seen by comparing the early universe with other places where a theory announces its own limits. A mathematical divergence may indicate that some quantity truly becomes infinite, but it can also signal that an approximation has been pushed beyond the domain in which it should be trusted. Classical physics once produced ultraviolet catastrophes in calculations of thermal radiation until quantum theory changed the description. The problem was not solved by accepting an infinite physical output as the final word. It was solved by recognizing that the old framework was incomplete under those conditions. Cosmology may face an analogous lesson near its earliest classical boundary. Although the required deeper theory is not yet experimentally established, there is another subtlety in the act of rewinding. Cosmic time is defined within a space-time model, so extending that time coordinate backward assumes that the model itself remains meaningful. As long as general relativity provides a valid description, this procedure is well defined, near a regime where quantum effects of gravity may become important. However, even the familiar concepts of smooth geometry and continuous time could require revision. The apparent endpoint, reached by classical extrapolation, might therefore represent more than an unknown event. It might mark the point where the language used to ask what happened earlier begins to lose its ordinary meaning. None of this invalidates the reconstruction up to that boundary. The earlier universe really was hotter and denser than the universe today, and that conclusion is supported independently by observation. The uncertainty enters only when the successful trend is extended into conditions far beyond direct experimental access. This distinction prevents two opposite mistakes. One is to treat the classical singular limit as proven physical creation from nothing. The other is to react to uncertainty near that limit by doubting the entire hot Big Bang history. Neither follows. The evidence remains strong over the range where the model is tested, while the extrapolation becomes less secure as it approaches the regime in which new physics is expected. The backward journey therefore has a layered character, close to the present. It is anchored by galaxies, expansion measurements, and well-tested gravitational physics. Deeper in the past, it is anchored by the microwave background, primordial nucleosynthesis, and particle physics. Earlier still, the reasoning depends more heavily on extrapolation. Temperature and density continue to rise, but observational access becomes increasingly indirect. Eventually, the classical equations point toward a state so extreme that their own assumptions can no longer be treated as unquestionable. This is the first major threshold in the origin problem. Rewinding the cosmos does not reveal a simple scene of the universe becoming smaller until it disappears. It reveals a sequence of physical regimes, each less familiar than the last, converging toward a mathematical boundary where classical spacetime can no longer be followed with confidence. The next question is therefore not merely what the universe was like at that boundary, but whether the boundary is a real moment in nature at all, or the place where the classical map reaches the edge of what it can describe. In classical cosmology, the word singularity does not name an object waiting at the beginning of the universe. It names a failure in the mathematical description of spacetime. When the equations of general relativity are extended backward under broad conditions, they can reach a boundary beyond which certain paths through spacetime cannot be continued. While quantities associated with density or curvature may grow without bound, the temptation is to treat that result as a literal scene, the entire universe compressed into a point of infinite density at the first instant of time. But the mathematics is more careful than that picture. A singularity is not something general relativity describes in the ordinary way. It is precisely where the theory stops providing a complete description. This distinction became especially important once cosmologists began to understand that the early universe was not simply a smaller version of the present cosmos, but a regime in which the assumptions of classical spacetime itself may eventually fail. General relativity is extraordinarily successful because it treats gravity as geometry. Matter and energy shape spacetime, and spacetime guides the motion of matter and light. In most situations, this framework gives precise, testable results. Yet the theory is classical. It assumes a smooth spacetime manifold, a continuous geometric structure that can be described without incorporating the quantum behavior expected at the smallest physical scales. When the equations are pushed toward extreme density and curvature, they do not suddenly acquire the quantum ingredients they were never built to contain. Instead, they continue according to their classical form, and that continuation can lead toward infinities. The appearance of an infinity is therefore ambiguous. It could mean that nature truly reaches a state with no finite density or curvature, or it could mean that the variables used by the theory have been driven beyond the range in which they remain physically meaningful. Physics contains other examples in which infinities reveal the limits of an approximation rather than the literal structure of reality. What makes the Big Bang singularity especially difficult is that there is no experimentally confirmed deeper theory ready to replace general relativity at that boundary. The singularity, therefore, remains both mathematically serious and physically uncertain. It cannot simply be ignored, because it emerges from powerful results within the classical theory. But it also cannot safely be turned into a complete account of cosmic creation. The modern understanding of singularities owes much to the recognition that they should not be defined merely as places where one chosen quantity becomes infinite. Coordinates can behave badly even when space-time itself remains regular, and apparent divergences can sometimes be removed by describing the geometry differently. A more robust idea focuses on geodesic incompleteness. A geodesic is the path followed by a freely moving particle or a ray of light when no non-gravitational force diverts it. If such a path reaches an endpoint after only a finite amount of proper time, or an equivalent measure, and cannot be extended any farther within the space-time, the geometry is called incomplete. That incompleteness is a stronger signal than a strange coordinate value. It says that the classical space-time itself has reached a boundary in the mathematical model. The famous singularity theorems developed in 20th century relativity showed that this kind of incompleteness is not merely a quirk of perfectly symmetric cosmological solutions. Under suitable physical and geometric conditions, singular behavior can arise quite generally. For cosmology, the implication was profound. The problem could not be dismissed simply by arguing that the real universe is irregular and therefore would avoid the idealized Big Bang singularity. Yet even these theorems do not describe what exists at the incomplete boundary. They establish limits on the extension of classical spacetime under their assumptions. They do not provide a microscopic picture of the boundary, nor do they prove that absolute nothingness lies on the other side. The difference between an endpoint of a theory and an endpoint of reality is therefore central. Suppose a clock is carried backward along a time-like path toward the classical Big Bang boundary. Within the model, only a finite amount of proper time may separate an observer from that boundary. This can sound like direct proof that time itself begins there, but what the result strictly says is that the particular classical spacetime cannot be extended indefinitely into the past along that path while preserving the assumptions of the theorem and the form of the geometry. Whether a more complete theory continues, the description in another way is left open. That continuation might resemble an earlier phase of spacetime. It might involve a transition in which the classical concept of time loses meaning temporarily. It might replace the singularity with a quantum state that does not have an ordinary geometric interpretation. It might even preserve a genuine beginning. General relativity alone does not decide among these possibilities. This is why cosmologists distinguish a singularity from an ordinary event. An event in relativity is part of space-time. It has a location in the four-dimensional geometry and can, at least in principle, stand in causal relation to other events. A singularity is not necessarily another event of that kind. In many formulations, it is better understood as a boundary where the space-time description cannot be continued. Calling it the first event can therefore smuggle in precisely what still needs to be established. The popular image of all matter occupying one infinitely small point creates a similar problem. In a homogeneous cosmological model, every region of space becomes denser as the scale factor decreases. The singular behavior is not a conventional point sitting somewhere inside a larger surrounding space. It is associated with the entire spatial geometry as the model is extended backward. There is no external room around it, and no ordinary center from which the universe later erupts. The classical limit is global, not a bomb site. This matters because the wrong picture makes the origin problem look simpler than it is. A point explosion invites the question of what surrounded the point and what triggered it. A singular boundary in spacetime raises a deeper question about whether concepts such as before, location, and duration remain valid at all. The scientific caution surrounding singularities does not make them unimportant. On the contrary, their importance comes from the fact that they expose where an otherwise successful theory becomes insufficient. If a calculation predicts a finite star, a measurable orbit, or a gravitational wave, the theory remains within a domain where its meaning is clear. When the same framework predicts that curvature becomes unbounded and geodesics terminate, it is signaling that something fundamentally different is required. The singularity is therefore less like a discovered object and more like a boundary marker drawn by the theory itself. It says that classical spacetime has been followed as far as the equations can reliably carry it. What lies beyond that marker is not supplied by the marker. There is also no guarantee that every proposed replacement removes all conceptual difficulties. A non-singular model must do more than erase an infinity from an equation. It must reproduce the successful history of the hot Big Bang, remain mathematically consistent, connect with known physics at lower energies, and ideally produce predictions that can be distinguished from competing scenarios. A bounce, a quantum origin, or an emergent phase gains no automatic credibility merely because it avoids a classical singularity. The burden shifts rather than disappears. The classical problem tells physics where a deeper theory is needed, but not which deeper theory is correct. This restraint becomes especially important when the singularity is used in claims about the beginning of time. If the classical boundary is taken literally, then ordinary temporal extension ends there, and the phrase before the Big Bang may have no meaning within that model. If the boundary is instead resolved by quantum gravity, the concept of an earlier state might return, perhaps in a form unlike ordinary cosmic time. Both possibilities remain open at the level of the singularity itself. The mathematics narrows the issue, but it does not close it. The Big Bang singularity is therefore one of the clearest examples of how a powerful equation can lead directly to a question it cannot answer. General relativity points backward toward a boundary where its classical geometry becomes incomplete. That is a profound result, but it is not yet a photograph of creation. The singularity may be a genuine beginning, or it may be the mathematical shadow cast by physics that has not yet been fully described. To move farther, cosmology has to cross from the language of classical spacetime into a regime where gravity and quantum theory can no longer be kept separate. Near the classical Big Bang boundary, the problem changes character. Earlier sections of cosmic history can be reconstructed by taking well-tested physics and applying it to hotter and denser conditions. But eventually the extrapolation reaches a regime where gravity itself can no longer be treated as purely classical. This threshold is associated with the Planck scale, named after Max Planck, and it marks not a known event, but a region where the separate frameworks of general relativity and quantum theory are expected to meet. The characteristic Planck time is roughly 10 to the power of minus 43 seconds, an interval so small that ordinary intuition offers little help. It does not mean that science has observed a clock ticking down to that exact instant. It means that combinations of the fundamental constants of gravity, quantum mechanics, and relativity define a scale at which the assumptions behind the usual description of spacetime are likely to become unreliable. Above that threshold in energy, or equivalently at correspondingly tiny scales, quantum fluctuations of geometry may become impossible to ignore. The difficulty is that the two great theoretical structures of modern physics were built for different domains. General relativity describes gravity through smooth spacetime geometry and has passed tests ranging from planetary motion to gravitational waves. Quantum theory describes matter and the other fundamental interactions with extraordinary precision, but it does so using a framework in which spacetime is usually treated as a background rather than as a quantum object in its own right. In most physical situations, this division causes no serious conflict because gravity is weak compared with the other interactions. Near the earliest moments of cosmic history, however, density and curvature become so extreme that the separation cannot be maintained. A theory that allows matter to behave quantum mechanically while forcing spacetime to remain perfectly classical is expected to become incomplete. This is the Planck wall in cosmology, not a literal barrier standing at a certain timestamp, but the limit beyond which current established theories no longer provide a single trustworthy language. The significance of this limit can be understood by considering what quantum behavior means elsewhere in physics. At microscopic scales, particles are not adequately described as tiny classical objects following perfectly defined trajectories. Their properties are represented by quantum states, probabilities, and fields that can fluctuate even in what would classically be called empty space. Applying comparable principles to gravity suggests that spacetime itself may acquire quantum uncertainty. Distance, duration, and curvature could cease to be sharply defined in the classical sense. A smooth geometry might emerge only after averaging over a deeper quantum structure. If that is true, then asking for the exact density or curvature at the earliest classical instant may be similar to asking for the precise shape of an ocean surface While ignoring that, at a sufficiently small scale, the continuous surface description has broken down into molecules. The analogy is imperfect, but the lesson is useful. A successful large-scale description does not have to remain fundamental at every scale. General relativity may describe the smooth behavior of spacetime in much the same way that fluid mechanics describes water, while a deeper quantum theory determines what spacetime becomes under extreme conditions. Several approaches attempt to provide such a theory, but none has yet received decisive experimental confirmation. String theory seeks a unified framework in which fundamental entities are extended rather than point-like, and gravity appears naturally among their possible excitations. Loop quantum gravity takes a different route, attempting to quantize geometric quantities themselves and suggesting that area and volume may acquire discrete structures at the deepest level. Other programs explore causal sets, asymptotic safety, emergent spacetime, and related ideas. Each changes the origin problem in a different way, but the existence of multiple frameworks is itself evidence of how open the question remains. A mathematically elegant theory is not enough. To become an established description of nature, it must connect with observations, reproduce the successes of general relativity and quantum physics where those theories work, and ideally predict effects that competing models do not. The Planck regime is difficult to test because its characteristic energies lie far beyond those directly reachable by present particle accelerators. Cosmology, therefore, becomes one of the few possible laboratories. The early universe may have operated at conditions that no terrestrial experiment can reproduce, and relics from that period could, in principle, preserve indirect evidence of quantum gravity. Yet the same cosmic expansion that makes the early universe accessible through its later consequences also stretches and dilutes many possible signals. By the time light can travel freely and the cosmic microwave background is released, the universe has already evolved enormously from the Planck regime. Any surviving imprint must pass through multiple later processes before reaching observation, which makes interpretation difficult. This is why statements about the earliest instant tend to carry much more uncertainty than statements about the later hot Big Bang. Physics can calculate primordial nucleosynthesis with confidence because the relevant interactions are comparatively well understood. It can model the cosmic microwave background with striking precision because the governing physics falls within tested domains. But when the clock is mathematically pushed toward the Planck scale, there is no experimentally confirmed equation that takes over and provides an equally secure continuation. The uncertainty is structural, not merely a lack of better measurements. The basic ingredients of the theory are unsettled. Even the concept of time may become part of the problem. In ordinary quantum mechanics, time typically functions as an external parameter against which a system evolves. In general relativity, time is woven into dynamical spacetime and can be affected by gravity. A theory of quantum gravity has to reconcile these very different roles. Some formulations suggest that the familiar flow of time might not be fundamental at all, but could emerge from relations among deeper quantum degrees of freedom. If so, asking what happened before the Planck regime may eventually require a different kind of question, one in which the ordinary sequence of earlier and later appears only after a classical spacetime has formed. This possibility does not prove that time is emergent, nor does it establish that the universe lacks a beginning. It simply shows why the problem cannot be settled by extending familiar intuition into a domain where the familiar definition of time itself may fail. The same caution applies to the word before. In a bouncing cosmology, an earlier contracting phase could make that word meaningful in something close to the ordinary sense. In a no-boundary proposal, the deep quantum regime could lack a simple temporal edge. In another theory, a genuine beginning might remain. The Planck wall does not select among these possibilities. It is the region where the choice has to be made by physics that is not yet empirically settled. There is also no guarantee that the true theory will resemble any of the current candidates in detail. Scientific history repeatedly shows that conceptual problems can be resolved in ways that were difficult to anticipate from the older framework. The quantum revolution did not merely adjust classical mechanics, it replaced some of its deepest assumptions. General relativity did not simply refine Newtonian gravity, it redefined gravity as geometry. Quantum gravity may require a comparable shift in how spacetime, causality, and temporal order are understood. That prospect makes the earliest universe scientifically difficult, but also unusually revealing. A successful theory would not only describe a tiny interval near the traditional beginning, it would explain how classical space-time emerges, why the hot Big Bang begins with the conditions it does, and perhaps whether the apparent singularity is removed, transformed, or preserved in a deeper form. Until such a theory is confirmed, the Planck scale remains the clearest marker of where current cosmology loses the right to speak with the same confidence it has at later times. The universe can be followed backward through radiation, nuclei, particles, and increasingly extreme geometry, but not indefinitely with known physics alone. At the Planck wall, the question of origins stops being a matter of running established equations farther into the past and becomes a question of what space-time is made of, how gravity behaves quantum mechanically, and whether time itself survives as a fundamental concept. The boundary is therefore not merely a gap in the timeline, it is the point where the timeline may cease to be the right object to extend. Inflation enters the story because the hot Big Bang, successful as it is, begins with conditions that seem surprisingly organized. The observable universe is remarkably uniform on large scales. Regions now separated by enormous distances share almost the same background temperature, even though a simple non-inflationary reconstruction suggests that some of those regions would not have had enough time to exchange light or matter before the cosmic microwave background was released. The geometry of the universe is also very close to spatially flat, a condition that becomes increasingly difficult to maintain when ordinary expansion is extrapolated backward without special initial conditions. Inflation was proposed as a way to address problems like these by inserting an earlier period of extraordinarily rapid expansion before the conventional hot phase. During inflation, the scale of space grows by an immense factor in a very short interval, so quickly that regions once close enough to influence one another can later become separated across distances far larger than the observable horizon of the early universe. In this picture, the uniformity seen in the cosmic microwave background is not an unexplained coincidence. It is the stretched remnant of a region that may once have been small enough for physical processes to smooth it out before inflation carried different parts far apart. The mechanism is usually described through a form of energy whose pressure can drive accelerated expansion. In simply models, that role is played by a scalar field, a quantity that has a value at every point in space and whose stored energy can dominate the dynamics of the early universe. If the field changes slowly enough, its energy behaves in a way that causes the scale factor to grow almost exponentially. The universe does not explode into empty surroundings. Space itself expands at an accelerated rate. Small regions are stretched to enormous size. Pre-existing curvature is diluted, and unwanted relics from still earlier conditions can become extremely sparse. Inflation, therefore, acts as a cosmic smoothing process, but it is not perfectly featureless. Quantum fluctuations in the inflationary field and in space-time can be stretched to astronomical scales. After inflation ends, those tiny variations can become the seeds of later density differences. Gravity then amplifies them over billions of years into galaxies, clusters, and the cosmic web. This connection between microscopic quantum fluctuations and the largest structures in the universe is one of the most striking features of the inflationary idea. The end of inflation is just as important as its beginning. Accelerated expansion cannot continue in the same way if the universe is to become the hot environment required by the later Big Bang history. The energy associated with inflation must be converted into particles and radiation through a process often described as reheating. Once that transition occurs, the universe enters the familiar hot, denser, expanding state in which particle interactions, primordial nucleosynthesis, and eventually the release of the cosmic microwave background can take place. For this reason, modern discussions often distinguish inflation from the hot Big Bang, rather than treating them as the same event. Inflation, if it occurred, belongs to an earlier phase. The hot Big Bang describes what follows when the universe becomes filled with hot matter and radiation. This distinction immediately weakens the old image of the Big Bang as the first instant. If a period of inflation precedes the hot phase, then the beginning of the hot Big Bang is already not the beginning of the entire physical story. Yet inflation does not automatically solve the origin problem. It can explain why a large region becomes smooth and nearly flat, and it can provide a mechanism for generating primordial fluctuations. But none of these achievements identifies the ultimate source of the inflationary state itself. A model can specify how inflation proceeds once the required conditions are present, while remaining silent about why those conditions exist. It can describe a field rolling through a potential without explaining where the potential, or the surrounding space-time came from. It can move the earliest well-described chapter backward without proving that the chapter has no earlier page. In this sense, inflation may transform the origin question rather than eliminate it. Instead of asking why the hot Big Bang began in such an orderly condition, the question becomes why inflation began, how long it had already been occurring, and whether the space-time supporting it extends still farther into the past. This is not merely a philosophical concern. Different inflationary models can have different past histories. Some allow inflation to continue indefinitely toward the future in parts of an expanding space-time, producing a patchwork in which inflation ends locally while continuing elsewhere. This idea is known as eternal inflation. Despite its name, future eternity does not necessarily imply an infinite past. A process can continue without end in one temporal direction while still having a boundary in the other. That asymmetry becomes crucial when inflation is discussed as a possible escape from a cosmic beginning. The fact that inflation can generate an immense or even endlessly reproducing future does not by itself show that it existed forever before the observable universe formed. There is also an observational limit. Inflation is strongly motivated by the large-scale properties of the universe and is consistent with important features of the primordial fluctuation pattern, but the exact physical mechanism remains uncertain. Many versions of inflation can reproduce similar broad observations while differing in their underlying fields. Energy scales, duration, and predictions for subtle signatures such as primordial gravitational waves or departures from simple Gaussian statistics. No single inflationary model has been established as the unique description of what happened. This matters because claims about what came before inflation depend on details that observations have not yet fixed. If the mechanism is uncertain, its extension into deeper time is even more uncertain. Still, inflation changes the conceptual landscape of the Big Bang in an important way. It shows that the hot, dense state can be the product of an earlier process rather than an unexplained initial condition. The universe observed through the microwave background may therefore be the aftermath of a transition, not the direct imprint of an absolute beginning. The term reheating itself carries this implication. A universe becomes hot because energy stored in the inflationary phase is transformed into a bath of particles and radiation. The familiar early fireball is then an outcome, what appears in older descriptions as the first state becomes. In this framework, a later state generated by physics acting before it. That does not mean the earlier phase is better understood than the hot Big Bang. Quite the opposite. The hot Big Bang rests on multiple direct and indirect observational pillars. Inflation reaches into a more remote regime and is inferred from the conditions it can explain and the patterns it can produce. Its broad success lies in organizing several otherwise puzzling features within a single dynamical idea. But the origin of inflation remains unsettled. The deeper the question moves, the more it approaches the same difficulty already encountered near the Planck wall. If inflation begins at energies where quantum gravity becomes important, then even the classical picture of an inflating spacetime may fail close to its own past boundary. A complete answer would have to explain not only the expansion of space, but the quantum origin or prior history of the spacetime that inflates. For that reason, inflation is best understood as a bridge between established early universe cosmology and the unresolved problem of beginnings. It may explain how a tiny region acquires the smoothness, flatness, and primordial fluctuations that later become the observable cosmos. It may place a rapid phase of expansion before the hot thermal history. It may even make the beginning of the hot Big Bang look less like creation and more like a conversion of energy from one cosmic regime into another. But once the bridge is crossed backward, the same question is waiting on the other side. Was inflation itself preceded by another state? Or does its space-time terminate at a boundary that requires new physics? The theory can push the frontier of the known farther into the past. Yet pushing a frontier backward is not the same as removing it. Inflation therefore changes where the mystery begins, without proving that the mystery has an end. The question of whether inflation can extend forever into the past becomes sharper when the geometry of expanding spacetime is examined directly. This is where the Borde-Guth-Vilenkin theorem enters the discussion. It is often presented in simplified form as a proof that the universe must have had a beginning, but that summary is too strong. The theorem establishes something more precise and more limited. In a broad class of spacetimes whose average expansion along certain past-directed paths is positive, those paths cannot be extended indefinitely into the past. In the language of relativity, the spacetime is past incomplete along those geodesics. That conclusion places a serious restriction on many models of eternal inflation, because a universe that keeps expanding on average cannot simply be assumed to stretch backward without limit under the same conditions. Yet past incompleteness is not the same thing as creation from nothing, and it is not the same thing as proving that time itself began at a first instant. The distinction begins with the meaning of a geodesic. In general relativity, freely moving particles and light follow paths determined by the geometry of spacetime. If one traces such a path backward and discovers that it reaches the edge of the spacetime after only a finite amount of proper time or a fine parameter, then the geometry is incomplete along that path. The theorem shows that this kind of incompleteness follows under a condition involving average expansion, without requiring the full machinery of the classical energy conditions used in older singularity theorems. That makes the result powerful. It applies to many inflationary settings, even when the detailed matter content is unusual, or the dynamics are not those of a simple textbook universe. The theorem, therefore, prevents an easy escape from the origin problem. It is not enough to say that inflation has always been happening, and therefore no deeper explanation is required. If the inflationary spacetime is expanding on average along the relevant trajectories, the theorem indicates that the classical description cannot be extended arbitrarily far into the past along them. Somewhere, the spacetime history governed by those assumptions runs out, but what lies at that limit is deliberately left open. The theorem does not say that the boundary is a singularity of infinite density. It does not say that the universe emerged from literal nothingness. It does not say that no earlier phase can exist. And it does not say that every conceivable cosmological model must possess the same kind of beginning. Its conclusion concerns geodesic completeness under a specific average expansion condition. If the assumptions fail, the theorem no longer forces the same result: a preceding contracting phase, a static phase, a quantum gravitational regime, or some other geometry might alter the average behavior enough to avoid direct application. Whether such alternatives are physically realistic is another question, but they are not ruled out merely by invoking the theorem. This is why the result is best understood as a boundary theorem rather than a complete origin theory. It says that many expanding spacetimes require additional past physics. It does not supply that physics. The distinction is easy to lose because ordinary language treats an incomplete past as if it must be an absolute beginning. In mathematics, however, incompleteness can mean that a particular description ends, while a larger or different description remains possible. A map of a coastline may end at the edge of the page without implying that the land itself ends there. In relativity, the analogy must be used carefully, because not every incomplete spacetime can be extended smoothly into something larger. Some boundaries may reflect genuine singular behavior. Others may signal that the variables or assumptions being used are no longer adequate. The theorem by itself does not decide which interpretation is correct for the earliest universe. This matters especially for inflation, because inflation is often imagined as a process that could reproduce itself eternally. In many models, inflation ends in some regions while continuing in others, potentially creating an enormous future in which new expanding regions repeatedly emerge. Such future persistence does not guarantee a past without boundary. A spacetime can be future eternal and still be past incomplete. The arrow of the construction matters. The theorem, therefore, separates two ideas that are easily blended together: eternal inflation toward the future and an eternal universe toward the past. The first may be possible within some models even if the second is not. That asymmetry is one reason the theorem has remained important in discussions of cosmic origins. It prevents the vastness of an inflationary future from being mistaken for evidence of an infinite past. At the same time, the theorem does not require the beginning to look like the classical Big Bang singularity. The past boundary of an inflationary region could be connected to a phase in which the average expansion is not positive. It could be preceded by contraction. As in some bouncing scenarios, it could emerge from a quantum state in which classical spacetime is not yet the right description. It could approach a nearly static configuration for an extended period. Or the boundary could indeed represent the start of the spacetime described by the theory. Each possibility requires additional assumptions beyond the theorem itself. The scientific problem, therefore, shifts from whether the inflationary geometry can simply be extended backward forever to what kind of structure can replace or precede the incomplete region. This shift is important because it turns the theorem into a constraint on model building. Any proposal for a universe with no beginning must show how it escapes the conditions that generate past incompleteness. And it must do so without losing agreement with the observed universe. A model cannot merely declare itself eternal. It has to demonstrate that its space-time dynamics and matter content actually support that claim. This is difficult. A contracting phase may introduce instabilities. A static past may be fragile. A quantum transition may depend on a theory of gravity not yet experimentally confirmed. A cyclic model may face problems with entropy or with maintaining consistency from one phase to the next. The theorem does not prove that these attempts fail, but it forces them to work harder. It narrows the easy options. The same caution applies when the theorem is used in philosophical or theological arguments. Its mathematical conclusion is about the extendability of geodesics in spacetimes satisfying an average expansion condition. Translating that into a claim about absolute creation adds steps that are not contained in the theorem. Physics may ultimately support a genuine temporal beginning, but that conclusion would require more than past incompleteness alone. It would require understanding the nature of the boundary and ruling out physically viable extensions or precursor regimes. At present, that deeper layer remains unsettled. There is another subtle point. The theorem does not depend on tracing the universe all the way back through a detailed thermal history. It uses the kinematics of expansion itself. This gives it a certain robustness, because its force does not rest on one specific inflationary potential or one particular model of matter, but that strength can also make the result sound more universal than it is. Average expansion is still an assumption, and the theorem addresses particular classes of geodesics under that condition. Cosmology contains proposed scenarios in which the far past is not, on average, expanding in the required sense. Those scenarios may therefore fall outside the theorem even if they later enter an inflationary phase. Whether they solve the origin problem or merely move it to a different structure has to be examined separately. In this way, the Borde-Guth-Vilenkin theorem resembles the broader pattern that has appeared throughout the search for the beginning. Every time cosmology seems to approach a final edge, the edge turns out to have a more careful meaning than ordinary language suggests. The hot Big Bang is not automatically creation. The classical singularity is not automatically a physical point. The Planck scale is not a measured first instant. Inflation is not automatically past eternal. And past incompleteness is not automatically proof of absolute nothingness before the universe. Each result is powerful because it removes some possibilities while leaving others open. The theorem does something especially valuable. It shows that inflation alone cannot be casually used to erase the question of a beginning. If the universe has been expanding on average through an inflationary history, then some earlier boundary or different regime is still required. The mystery is not eliminated. It is compressed into a sharper demand. The next theory must explain what replaces the past edge of the inflationary spacetime, and whether that replacement is another phase of cosmic history or the deepest boundary time can possess. A big bounce begins with a reversal of the usual picture. Instead of tracing expansion backward until spacetime ends at a singular boundary, the history continues into an earlier phase in which the universe is contracting. Density and temperature rise as that contraction proceeds. But rather than diverging without limit, the dynamics change near an extreme quantum regime. The contraction slows, reaches a minimum scale, and turns into expansion. In that picture, the Big Bang is not the birth of the universe from nothing. It is the transition between two phases of cosmic evolution. The familiar hot, dense state still appears, and all of the later evidence for the hot Big Bang still has to be reproduced. But the singularity itself is replaced by a bounce. This idea is attractive because it directly addresses the point where classical general relativity becomes incomplete. If the singularity is a sign that the classical description has been pushed too far, then a theory of quantum gravity might alter the equations before density and curvature become infinite. The essential question is whether gravity, once treated quantum mechanically, can become effectively repulsive under the right conditions. In ordinary circumstances, gravity draws matter together. near the extreme densities associated with a possible bounce. However, some quantum cosmological models predict corrections that change the behavior of spacetime enough to prevent unlimited collapse. One of the best-known examples comes from loop quantum cosmology, a simplified cosmological application of ideas from loop quantum gravity. In this framework, geometric quantities are not treated as perfectly continuous all the way down. The quantum structure of spacetime modifies the classical equations when density approaches a characteristic high value. Instead of continuing toward a zero-scale factor and infinite density, the universe can reach a smallest non-zero size and then re-expand. The classical singularity is replaced by a quantum transition. This does not mean that loop quantum cosmology has been experimentally confirmed. It remains a theoretical framework, and the precise relation between simplified cosmological models and a complete theory of quantum gravity is still under investigation. Yet it provides an explicit example of how a singular beginning can disappear without abandoning the successful hot Big Bang history that follows. The contracting phase before the bounce would not necessarily resemble the universe seen today played backward like a film. A realistic pre-bounce cosmos would depend on what forms of matter and energy dominate, how anisotropies evolve, how quantum effects become important, and whether large structures survive at all. If ordinary galaxies existed in a very distant contracting era, they would eventually be disrupted as density rose. But many bounce models do not require a simple mirror image of the present universe. The pre-bounce state may be smoother, more exotic, or governed by fields that have no obvious late-time counterpart. What matters is that spacetime has an earlier branch. Cosmic history does not terminate when the hot expanding phase is traced backward. It passes through a regime where the sign of the expansion rate changes. That possibility changes the meaning of the Big Bang in a very specific way. The hot beginning becomes similar to a phase transition. Water can move from liquid to ice without ceasing to exist, and a material can change structure while remaining part of a continuous physical history. A cosmic bounce would be far more fundamental than those familiar transitions, because the geometry of spacetime itself is involved. But the conceptual shift is comparable. The event marks a change of regime rather than creation from absolute absence. The difficulty is that replacing a singularity mathematically is only the first requirement. A successful bouncing model has to explain how a contracting universe reaches the bounce without becoming unstable. Contraction tends to amplify certain irregularities. Small differences in directional expansion can grow rapidly, threatening the smooth and nearly isotropic conditions required after the bounce. Some models introduce special forms of matter or a slowly contracting phase to suppress these effects, while others rely on quantum corrections near the transition. Each solution creates additional questions about consistency and initial conditions. A bounce must also produce the right primordial fluctuations. The observed universe contains a very specific spectrum of density variations, recorded most clearly in the cosmic microwave background. Inflation provides one mechanism for generating those fluctuations from quantum processes during rapid expansion. A bounce in cosmology needs an alternative account, or it must combine a bounce with a later period of inflation. Some scenarios attempt to generate the observed spectrum during contraction, then carry those perturbations through the bounce into the expanding phase. That transfer is delicate. If the bounce alters the perturbations too strongly, the later universe may no longer match observation. If it preserves them in the wrong way, the predicted cosmic microwave background can differ from what is measured. The bounce, therefore, cannot be judged only by whether it removes an infinity. It must survive the full observational history of the universe. There is also the question of entropy. In ordinary thermodynamics, entropy tends to increase. A contracting universe that precedes the present expansion must therefore explain how the thermodynamic arrow of time behaves across the bounce. Does entropy continue increasing through the transition, making the pre-bounce branch thermodynamically very different from the present one? Does the arrow of time reverse relative to the bounce? Can repeated bounces occur without entropy, accumulating from cycle to cycle? These questions become especially important in cyclic models, but even a single bounce has to confront them. Time itself may remain continuous through the transition in some models, while in others the quantum regime could make ordinary temporal description less straightforward. The word before is therefore more meaningful in a bounce than in a strict classical singularity, but it may still not refer to an ordinary environment governed by familiar clocks and geometry. Another challenge comes from evidence. A pre-bounce phase can be scientifically valuable only if it leaves consequences that can, at least in principle, distinguish it from inflationary or singular histories. Possible signatures include unusual patterns in primordial fluctuations, distinctive non-Gaussian correlations, or a background of gravitational waves with properties different from those predicted by common inflationary models. None of these signatures has yet provided decisive evidence for a bounce. This absence does not rule the idea out, because many models predict effects that are small or difficult to isolate, but it prevents the bounce from being treated as an established description of cosmic history. The current position is therefore asymmetric. The hot Big Bang is strongly supported. The classical singularity appears when general relativity is extrapolated backward. Quantum gravity is expected to become important before that extrapolation can be trusted indefinitely. A bounce is one plausible way quantum gravity might resolve the problem. But it is not the only one, and no observation has selected it as the correct answer. That uncertainty is scientifically useful because it clarifies what any deeper theory must accomplish. It must remove or reinterpret the classical breakdown, reproduce the known hot phase, generate the observed primordial conditions, remain stable through extreme evolution, and make contact with measurements. The Big Bounce is compelling not because it has already passed all of these tests, but because it demonstrates that a beginning is not the only mathematical possibility. Once classical spacetime is no longer treated as fundamental, the singularity can be replaced by dynamics. The past can acquire another branch. The Big Bang can become an event inside history, rather than the edge of history. If such a model were eventually supported, then the oldest accessible question would change. Cosmology would no longer ask only how expansion began. It would ask what the contracting universe was like, how long it existed, what shaped its approach to the bounce, and whether information from that earlier phase survived the transition. The origin problem would not disappear. It would move from a first moment to a deeper continuity, where the present universe might carry faint traces of a cosmos that existed before its hot expansion began. A universe before the Big Bang would not necessarily look like a reversed version of the present cosmos. The idea of a pre-bounce phase is often described in simple terms as contraction followed by expansion, but the physical meaning of that contraction depends on what fills the universe, how geometry evolves, and which processes dominate as density increases. If the earlier cosmos begins in a large and relatively dilute state, distances between widely separated regions gradually shrink. Radiation becomes more energetic as its wavelengths are compressed. Matter becomes denser. Gravitational interactions strengthen as structures are drawn into an increasingly compact cosmic background. Yet the familiar hierarchy of planets, stars, galaxies, and clusters would not survive indefinitely. Long before the bounce, large structures could merge, collapse, or be disrupted. At still higher density, atomic and nuclear matter would be subjected to conditions increasingly unlike anything in the present universe. The closer the system moves toward the quantum gravitational regime, the less useful ordinary astronomical imagery becomes. What survives is not necessarily a landscape of galaxies falling together, but a changing set of fields, perturbation, and geometric degrees of freedom moving toward an extreme transition. The geometry itself is central in an expanding universe. Small irregularities in the rate of expansion can often become less important under the right conditions. During contraction, the behavior can reverse. Differences in how rapidly separate directions shrink may grow, producing anisotropy, a departure from the same expansion or contraction rate in every direction. This is a serious challenge because observations show that the early universe after the hot Big Bang was extraordinarily smooth and nearly isotropic on large scales. A viable pre-bounce model therefore needs a mechanism that prevents contraction from becoming chaotically uneven before the transition is reached. Some scenarios introduce a special contracting phase in which the dominant energy component has properties that suppress anisotropies more quickly than they can grow. Ekpyrotic models use a form of slow contraction with an unusually stiff effective equation of state, allowing the background to become smoother as the bounce approaches. Other approaches rely more heavily on quantum gravitational corrections near the transition itself. In either case, the pre-Big Bang universe cannot be arbitrary. Its dynamics must prepare conditions compatible with the universe that emerges afterward. Matter content presents a second difficulty. If the contracting cosmos contains ordinary radiation, matter, black holes, and other remnants from an earlier era, their densities rise as the scale factor decreases. Radiation becomes increasingly important because its energy density grows rapidly during contraction. Black holes could merge and become dynamically significant. Particle interactions that are negligible in a dilute universe could return to thermal equilibrium at high temperature. Eventually, the distinction between familiar matter components may break down as energies approach regimes where the underlying particle physics is uncertain. Some models simplify this picture by assuming that a scalar field dominates the contraction, allowing its energy to control the geometry and suppress unwanted behavior. But such fields are theoretical ingredients, not observed relics from a known earlier universe. Their purpose is to create a mathematically consistent route into the bounce. Whether nature ever used such a route remains open. The most intriguing question is not simply what the earlier phase contained, but whether anything from it could survive. A bounce that completely erases prior information would make the pre-Big Bang universe almost impossible to test. The earlier phase might exist mathematically, yet the expanding branch would carry no recoverable memory of it. A more interesting possibility is that some perturbations pass through the transition. Tiny variations in density, curvature, or fields generated during contraction could be transferred into the expanding universe and later influence the formation of cosmic structure. In that case, the sky could contain a fossil record from before the hot Big Bang. The challenge is that the transfer through the bounce is highly model-dependent. Classical equations may fail precisely where the matching has to occur, and different quantum gravity frameworks can evolve perturbations differently. A fluctuation that grows during contraction may be suppressed at the bounce, mixed with another mode, or transmitted into expansion with altered amplitude and phase. Small changes in the microscopic theory can therefore change the predicted observable universe. This makes the problem difficult but also potentially testable. If a particular bounce mechanism produces a characteristic spectrum of primordial fluctuations, a specific pattern of non-Gaussian correlations, or a distinctive gravitational wave background, observations could favor or exclude that mechanism. Information can also be understood more broadly than density perturbations. The thermodynamic state of the earlier universe may matter. Entropy is especially troublesome because ordinary physical processes tend to increase it. If the pre-bounce cosmos has a long history, it may already contain enormous entropy by the time contraction begins. Compressing that entropy into a small volume could create conditions very different from the smooth, low-entropy state inferred for the early expanding universe. A bounce model must therefore explain how the thermodynamic arrow is carried across the transition, or how the relevant entropy is reorganized. Some proposals attempt to make the contracting and expanding branches symmetric around the bounce. Others allow the arrow of time to point away from the bounce in both directions, so that what counts as the thermodynamic future differs on either side. Still others accept an asymmetric history. None of these possibilities is observationally established, and each carries conceptual consequences for what it means to call one side before and the other after. The word before may itself become subtle. If time remains a smooth parameter throughout the bounce, then the contracting phase can be ordered in the ordinary way. Events occur. Contraction proceeds. The minimum scale is reached, and expansion follows, if the transition is genuinely quantum gravitational. However, classical time might cease to function normally near the bounce. The earlier and later branches could be connected by a quantum state whose description does not resemble a sequence of moments. In that case, the pre-Big Bang universe could still be physically related to the present one, even if the connection is not a simple continuation of classical time. This possibility complicates the intuitive image of a universe shrinking to a minimum size and then springing outward. The underlying transition may be less like a mechanical rebound and more like a change in the quantum state of geometry. Another question concerns how much of the earlier universe could influence the present one. During an expanding phase, causal horizons limit which regions can communicate. A contracting phase has its own horizon structure, and depending on the model, regions that are now widely separated may once have shared causal contact before the bounce. This could help explain large-scale uniformity without invoking the same inflationary mechanism used in standard scenarios. But the benefit comes with new requirements. The contraction must last long enough, remain stable enough, and generate the right spectrum of fluctuations. It must then pass those fluctuations through the bounce without producing excess irregularity. Every apparent solution, therefore, introduces a chain of conditions that must all survive comparison with observation. The pre-Big Bang universe is not unconstrained simply because it lies beyond direct sight. Its possible forms are restricted by the state of the universe that emerges from it, the smoothness of the cosmic microwave background, the nearly scale-invariant distribution of primordial fluctuations, the abundance of light elements, and the later growth of cosmic structure all act as filters on what the earlier phase could have been. A contracting universe that produces too much anisotropy, too much entropy, or the wrong fluctuation pattern cannot hide behind the bounce. Its failures would be carried into the expanding cosmos. This is where speculation returns to science. A pre-Big Bang phase is meaningful only if the theory specifies how it connects to measurable consequences. The most ambitious versions of bounce cosmology therefore search for relics that could have crossed the transition, altered large-scale power in the cosmic microwave background, unusual correlations among primordial perturbations, or gravitational waves shaped by contraction rather than inflation. None has yet provided a decisive signature. The absence of confirmation keeps the earlier universe hypothetical, but not shapeless. It can be studied through the conditions required for survival across the bounce. If any part of the present cosmos does preserve such a memory, then the Big Bang would not mark the erasure of all prior history. It would mark a narrow passage through which only certain forms of information were able to emerge. A cyclic universe replaces a single cosmic beginning with repetition. Instead of one expansion emerging from an absolute first moment, the history passes through a sequence of large-scale phases in which expansion is followed by contraction. Contraction approaches an extreme transition, and a new expansion begins. In this picture, the hot Big Bang belongs to the opening of the present cycle rather than to the birth of all existence. The idea has appeared in many forms, and the details differ greatly, but the central attraction is easy to see. If the universe can move through repeated phases, then the question of what came before the Big Bang receives a concrete answer: another cosmic era. That answer, however, creates a demanding set of physical problems. A cycle must do more than turn around. It must explain how a universe that has accumulated structure, radiation, entropy, and irregularity can pass through contraction and still produce a new expanding phase that resembles the remarkably smooth early universe inferred from observation. The transition has to be stable. The thermodynamics has to make sense. The primordial fluctuations have to emerge with the right properties. And if the process repeats indefinitely, each cycle has to avoid becoming less viable than the one before it. The simplest verbal sequence, expansion, followed by contraction, followed by expansion, therefore hides most of the real difficulty. During an expanding era, matter spreads out, stars form and die, black holes grow, and entropy increases. If expansion eventually reverses, those accumulated products do not simply vanish. They become part of the contracting universe. As distances shrink, radiation blue shifts and grows more energetic. Matter density rises. Gravitationally bound structures interact within an increasingly compact geometry. Any departures from perfect uniformity can become dynamically important. Without a mechanism to control these effects, contraction can become highly anisotropic and chaotic rather than producing the smooth approach required for a clean transition. This is one reason modern cyclic models often do not imagine a straightforward reversal of the present universe. They introduce special phases designed to reshape the cosmos before the next expansion begins. Ekpyrotic cosmology is one important example. In an ekpyrotic phase, the universe contracts very slowly, while a form of energy with a particular effective pressure dominates the dynamics. Under the right conditions, this slow contraction can suppress spatial curvature and anisotropy relative to the dominant energy component. The result is a universe that becomes smoother and flatter as it contracts, rather than more disordered in the geometrical sense. That behavior makes ekpyrotic contraction conceptually comparable to inflation in one important respect. Inflation smooths the universe during accelerated expansion. Ekpyrosis attempts to smooth it during controlled contraction. The mechanisms are different, and the observational predictions need not be identical, but both are responses to the same broad challenge, explaining why the early expanding universe begins so homogeneous across enormous scales. In cyclic versions of the idea, the ekpyrotic phase can occur before a bounce or transition that initiates the next expanding cycle. The Big Bang then becomes a recurring boundary between phases. Yet even if contraction successfully smooths the geometry, the bounce itself remains a critical point. Classical general relativity tends to drive a contracting universe toward a singularity. A cyclic model therefore needs some process that prevents infinite density and connects contraction to expansion. Depending on the framework, that process may rely on quantum gravity, modified gravitational dynamics, additional fields, or other mechanisms beyond the simplest classical description. The transition must be mathematically consistent and physically stable. It must not create uncontrolled fluctuations or instabilities that destroy the smooth conditions established during contraction. It must also transfer or regenerate the perturbations that later seed galaxies. A model that solves the singularity problem but fails to reproduce the observed pattern of cosmic structure has not completed the task. Entropy presents an even deeper obstacle. In ordinary thermodynamics, entropy tends to increase. Each cycle contains irreversible processes, stars radiate, matter collapses, black holes form, energy is redistributed, and information becomes spread across increasing numbers of microscopic states. If every new cycle simply inherits all of that entropy, then successive cycles cannot be exact copies. They may become larger, longer, or otherwise different, and tracing them backward can eventually raise the question of whether the sequence itself still requires some earliest low-entropy state. This difficulty has challenged cyclic cosmologies for a long time. Modern proposals attempt to handle it in different ways. For example, by allowing enormous expansion to dilute entropy density before the next contraction, or by arranging the cycles so that only certain regions or degrees of freedom participate in the transition. But no simple rule removes the thermodynamic problem without further assumptions. The arrow of time remains tied to it. If entropy increases from cycle to cycle, then the cycles possess a preferred temporal direction, even if the large-scale geometry repeats. A universe can be cyclic in size without being perfectly cyclic in thermodynamic history. This distinction matters because repetition can otherwise create the illusion that time has become a closed loop. Most cyclic cosmologies do not require individual events to recur exactly. They propose recurring phases of cosmic evolution, not an identical replay of every star and galaxy. The present cycle could therefore differ profoundly from any earlier one while still sharing the same broad sequence of contraction, transition, and expansion. Stability adds another layer. A mechanism that works for one carefully chosen set of conditions must also survive small disturbances. If tiny deviations grow from cycle to cycle, the repeating history can break down. Fields that drive contraction have to evolve in a controlled way. The bounce has to occur without pathological behavior. The expanding phase has to enter conditions compatible with a hot Big Bang. If inflation is included after the bounce, the model must explain how that inflation begins. If inflation is not included, the contracting phase must account for the observed primordial spectrum by another route. Each choice shifts where the burden lies, but it does not remove the burden. Cyclic models are therefore not simply alternatives to inflation. Some are built to replace inflation, some incorporate inflation, and others address a different layer of the origin problem. Their common feature is the refusal to identify the current hot Big Bang with an absolute beginning. This creates a useful scientific question about observables. If the present universe emerged from a previous contracting phase, then the primordial perturbations may contain a different statistical pattern from those generated in standard inflationary scenarios. The relative strength of fluctuations across scales, their correlations, their deviations from simple Gaussian behavior, and the spectrum of primordial gravitational waves can all become possible discriminants. A cyclic theory becomes scientifically stronger when it predicts something that cannot be freely adjusted to imitate every competing model. The challenge is that many early universe scenarios are flexible, and some observational signatures can overlap. A feature in the cosmic microwave background that appears suggestive in one model may also arise from a different mechanism. Evidence therefore has to be both distinctive and robust before it can support the claim that the universe passed through earlier cycles. No such decisive signature has yet established cyclic cosmology as the history of the real universe. The idea remains a family of theoretical possibilities rather than an observational conclusion. Even so, cyclic models reveal something important about the logical structure of the beginning problem. The hot Big Bang does not force cosmic history to have only one side. General relativity produces a classical singular boundary under ordinary assumptions. But new dynamics can be proposed that replace the boundary with a transition. Once that step is allowed, the earlier branch need not be a single contracting episode. It can become part of a much longer sequence. Yet an infinite sequence of cycles does not automatically solve every question about origins. If the cycles change systematically because entropy accumulates, the past may still behave differently from the future. If the bounce depends on quantum gravity, the deepest mechanism remains uncertain. If the cyclic phase itself is unstable, the repetition may not extend indefinitely. And if the model requires special initial conditions to begin cycling, the origin question has merely moved to those conditions. The strength of cyclic cosmology is therefore not that it has already removed the beginning. Its strength is that it demonstrates how much physical structure can exist between the hot Big Bang and the concept of absolute creation. A Big Bang can mark the start of one era while remaining embedded in a longer cosmic history. The deeper question then becomes whether the repetition can be made complete. Stable, thermodynamically consistent, and observationally distinct enough to survive as more than an elegant possibility, the Hartle Hawking no-boundary proposal approaches the origin problem from a direction very different from a bounce or a cyclic universe. Instead of placing another classical phase before the hot Big Bang, it asks whether the demand for a first temporal edge is itself the wrong demand. The proposal was developed by James Hartle and Stephen Hawking as a quantum cosmological condition for the universe as a whole. Its central idea is subtle near the deepest quantum regime. The distinction between space and time may cease to resemble the distinction experienced in the later classical universe. So the cosmos could be finite in an appropriate description without possessing a simple past boundary. This is often compared with the surface of Earth. The surface has a finite area, yet there is no edge where the surface suddenly stops. Travelling north eventually reaches the pole, but the pole is not a cliff beyond which the surface disappears. The analogy is only partial, because the no-boundary proposal concerns the geometry of spacetime in quantum gravity rather than an ordinary two-dimensional surface. But it captures the intended shift. A universe can be limited in extent without requiring a boundary in the ordinary sense. The proposal begins from the idea that quantum mechanics should apply not only to particles and fields inside the universe, but in some form to the universe itself. In ordinary quantum theory, a system can be described by a wave function that assigns amplitudes to possible configurations. Hartle and Hawking extended that logic toward cosmology by considering a wave function of the universe. Rather than asking for a classical state at a first moment and then evolving forward from it, the proposal attempts to define the quantum state through a sum over possible geometries. In simplified terms, different possible space-time histories contribute to the quantum description, and the no-boundary condition restricts those histories so that they remain regular and compact in the deep quantum regime. The remarkable consequence is that the classical picture of time can emerge only after the universe has moved away from that regime, near what would otherwise be called the beginning. The geometry may behave more like space than like ordinary time. This is where the phrase imaginary time is sometimes introduced. In technical treatments, a mathematical transformation can turn the time coordinate into a form that resembles an additional spatial direction. The phrase does not mean that time is fictional. It is a method used to describe certain quantum gravitational geometries more smoothly. In the no-boundary picture, the earliest regime can then avoid the sharp singular edge produced by classical general relativity. The geometry closes off smoothly instead of terminating at a point of infinite curvature. If a later classical universe emerges from that quantum state, time, as normally understood, becomes meaningful only after the transition into the classical regime. This changes the question of what happened before. If ordinary time does not extend through the deepest part of the geometry in the familiar way, then before may not refer to another earlier moment at all. The problem becomes analogous to asking what lies north of the North Pole. The question uses a direction that ceases to continue in the expected form. Again, the analogy must not be taken literally. The no-boundary proposal is not a map of the universe folded into a sphere, and it does not claim that physical time is simply another spatial coordinate everywhere. Its purpose is to show how quantum geometry could remove the need for a conventional initial edge. This is fundamentally different from a bounce. In a bounce scenario, there is usually an earlier contracting branch, so the word before retains a comparatively ordinary meaning. In the no-boundary approach, there may be no prior classical branch at all. The deep quantum region is not necessarily an earlier universe. It is a different kind of regime from which classical spacetime emerges. That makes the proposal especially relevant to the possibility that time itself is not fundamental. If time appears only when the universe becomes sufficiently classical, then asking for its absolute beginning may resemble asking when a property emerged rather than when an object was created. The physical meaning of this emergence is still difficult. A theory of quantum cosmology has to explain why a particular classical history becomes likely, why the universe later resembles the one observed, and how ordinary causal order arises from a more fundamental description. The no-boundary proposal was designed as an attempt to address precisely such questions by specifying a quantum state without imposing arbitrary data on a first classical surface. Yet the proposal does not eliminate uncertainty. Different mathematical formulations and choices in quantum cosmology can lead to different predictions, and the treatment of the gravitational path integral, the sum over possible geometries, is technically difficult. There is no direct experiment that has confirmed the no-boundary condition as the actual initial state of the universe. It remains a theoretical proposal rather than an observational fact. Its value lies partly in demonstrating that the origin problem can be reformulated without requiring a singular first instant. The proposal also has implications for inflation. In some treatments, the no-boundary wave function can assign probabilities to different inflationary histories, linking the quantum origin of the universe to later periods of accelerated expansion. This connection is important because a viable model cannot stop at removing the singularity. It has to feed into a universe that becomes large, smooth, nearly flat, and capable of producing the primordial perturbations later observed in the cosmic microwave background. The no-boundary idea, therefore, attempts to provide a quantum starting condition for histories that can eventually resemble the hot Big Bang universe. But the precise probabilistic predictions are subtle, and there has been continuing debate over which histories are favoured and how the mathematical framework should be defined. These debates are not minor details. They determine whether the proposal can become more than an elegant way of avoiding an edge. A successful theory must connect the deep quantum geometry to measurable features of the universe. That requirement places the no-boundary proposal alongside bounce and cyclic models in one important respect. All of them must eventually return to observation. A quantum geometry with no first edge is scientifically useful only if it yields a later universe whose properties can be compared with data. The cosmic microwave background, primordial fluctuation, the possible spectrum of gravitational waves, and the large-scale geometry of the universe are among the places where different early universe proposals might leave distinct consequences. At present, no observation has uniquely selected the Hartle Hawking picture. This uncertainty should not be confused with weakness in the hot Big Bang model. The no-boundary proposal concerns a much earlier and more speculative layer. The later hot, dense phase remains supported regardless of whether the deeper origin is a bounce, a boundary, a smooth quantum cap, or something not yet imagined. What changes is the interpretation of the earliest limit. Classical general relativity suggests a singularity. The no-boundary approach replaces that singularity with a regular quantum geometry and, in doing so, challenges the assumption that every finite history must possess a first moment resembling all later moments. The conceptual consequence is quiet but profound. A universe may have a finite past extent in the relevant mathematical description, while lacking a first instant that functions like the first frame of a film. Time may emerge gradually from a regime in which the usual distinction between temporal and spatial directions is not yet established. The origin then becomes less like an event, and more like a change in the character of geometry itself. This does not prove that time had no beginning. It changes what a beginning could mean. The no-boundary proposal leaves cosmology with a possibility that is neither an eternal classical past nor a creation event at a singular point. The The universe could be self-contained in a quantum sense, with no external moment required before its earliest geometry and no sharp temporal edge waiting behind the hot Big Bang. In that picture, the search for what came before reaches not another era, but a place where the word before may no longer be part of the physics. A past eternal universe removes the beginning in a different way from both a bounce and the no-boundary proposal. Instead of passing through an earlier contracting phase or replacing the first moment with a quantum geometry, an emergent universe scenario imagines that the cosmos existed for an indefinitely long time in some earlier state, before entering the expansion that eventually leads to inflation and the hot Big Bang. The word emergent is important because the familiar universe is not assumed to appear from nothing. It develops out of a prior condition that can be nearly static, slowly evolving, or otherwise very different from the hot expanding cosmos observed later. In the simplest versions, the early universe hovers near a stable configuration for an arbitrarily long past duration. At some point, a change in the dynamics allows expansion to begin, perhaps followed by inflation and then by the ordinary thermal history. If such a model were physically viable, there would be no first instant of cosmic time in the classical sense. The universe would have a history extending without bound into the past, yet the phase recognizable as the hot Big Bang would still possess a beginning. This distinction makes emergent cosmology one of the clearest examples of why the Big Bang need not coincide with the beginning of everything. The appeal of the idea is immediate. A universe that has always existed appears to avoid the singular boundary produced by straightforward backward extrapolation of classical expansion. It also shifts the question of initial conditions. Instead of asking why the universe suddenly appears in an extremely special state, the model can attempt to explain how a long-lived earlier configuration gradually evolves into the conditions required for inflation or hot expansion. But the apparent simplicity hides a difficult requirement. An eternal past is useful only if the earlier state is stable enough to survive for an unlimited duration. Even a tiny instability becomes dangerous when given infinite time to grow. A configuration that can persist for 1 billion years but eventually collapses is not past eternal. A state that is perfectly balanced only when parameters are tuned with extreme precision may simply relocate the initial condition problem rather than solve it. The original emergent universe proposals, therefore, focus heavily on finding cosmological solutions that are non-singular and sufficiently stable in the far past. One common starting point is a universe that approaches an Einstein static state, a configuration in which expansion is balanced by the gravitational effects of matter and other forms of energy. The classical Einstein static universe has a long history in cosmology, but it is famously unstable under ordinary perturbations. A slight change in density or expansion can cause it to move away from equilibrium rather than remain fixed. Emergent models attempt to modify this situation using scalar fields, unusual matter components, altered gravitational dynamics, or carefully chosen conditions that make the early phase more resistant to disturbance. The aim is not merely to hold the universe still, it is to create a state that can exist indefinitely in the past, and yet later leave that state without requiring an unexplained external trigger. Those two demands pull in opposite directions. Perfect stability makes departure difficult. Easy departure makes eternal survival difficult. This tension is one of the central problems of the entire class of models. The transition to expansion must also occur in a controlled way. If the universe sits in a nearly static phase and then evolves into inflation, the mechanism has to generate the right energy conditions and the right primordial perturbations. Inflation cannot simply be attached as a label. Its onset has to follow from the dynamics of the earlier state. If inflation is omitted, the emergent phase itself must somehow explain the large-scale smoothness, flatness, and fluctuation spectrum that inflation was designed to address. Either choice adds constraints. A past eternal model therefore has to reproduce the same later universe that every alternative origin theory faces. It must enter a hot, dense phase, allow primordial nucleosynthesis, generate a cosmic microwave background with the observed properties, and seed the structures that later become galaxies. Avoiding a singularity does not reduce those obligations. It adds another one. The model must remain consistent through an infinite or effectively unlimited past. The behavior of fluctuations becomes especially important. A static or slowly evolving universe can accumulate perturbations over time. Quantum fluctuations, thermal fluctuation, or classical irregularities may grow rather than remain harmless. If the past is infinite, even processes with extremely low probability can become relevant. A model that relies on a delicate equilibrium can be destabilized by the very fluctuations that quantum theory says should never vanish completely. This is one reason past eternal cosmologies are difficult to construct. The question is not whether equations can be written down that avoid an initial singularity. The harder question is whether the corresponding universe remains physically sensible when all relevant perturbations are included. Geodesic completeness provides another test, to say that a model is past eternal in a meaningful relativistic sense. It is not enough for a chosen time coordinate to extend toward negative infinity. Freely moving observers and light rays must also be extendable through the entire past without running into an incomplete boundary. Some cosmological solutions can look eternal in one variable while still hiding geodesic incompleteness. The same care that applies to singularity theorems therefore applies here. A true past eternal model has to show that its spacetime does not merely postpone the boundary behind a change of coordinates. This is also where the Bordeguth-Vilenkin constraint becomes relevant. A universe that is expanding on average along the relevant trajectories cannot simply be extended indefinitely backward under the theorem's assumptions. Emergent scenarios attempt to evade this by arranging a far past phase whose average expansion is not positive in the required sense. A sufficiently static or non-expanding past can therefore fall outside the theorem's direct conclusion. This is not a loophole in the mathematics. It means the model changes the physical assumption on which the theorem depends. But escaping the theorem does not prove that the model is correct. It only keeps the possibility open. The resulting universe must still pass the tests of stability, quantum consistency, and observation. Thermodynamics adds a quieter difficulty. A universe with an infinite past has had an infinite amount of time in which entropy-producing processes might occur. If the early state contains ordinary matter interacting in ordinary ways, why has it not already evolved toward maximum entropy? Why does a low-entropy configuration remain available to produce the structured universe? Observed later. Some emergent models reduce this concern by making the far-past state extremely simple, cold, or dominated by fields with limited available degrees of freedom. Others depend on special dynamics that suppress ordinary entropy production until the expansion phase begins. But the problem does not disappear automatically when the singularity is removed. An eternal past requires an account not only of geometry but of why irreversible processes have not exhausted the system before the observable cosmic history begins. This connects the origin question to the arrow of time. If time extends without beginning, then the observed direction in which entropy increases must arise from conditions that are not themselves explained by a first low-entropy moment. The theory must find another reason for temporal asymmetry. There are also versions of emergent cosmology in modified theories of gravity, where the equations differ from general relativity at high curvature or in special regimes. These modifications can sometimes support stable past-eternal states that classical gravity does not allow. Yet every alteration of gravity carries a burden of its own. It must reduce to general relativity where general relativity has been tested. Avoid introducing unphysical instabilities, and ideally produce predictions that distinguish it from competing theories. A past eternal solution that exists only because the gravitational equations have been adjusted is scientifically interesting, but it becomes compelling only if the adjustment is independently justified and observationally successful. The same is true for models built from exotic fields. Mathematical possibility is the first filter, not the last. The broader lesson is that the absence of a beginning is not automatically easier to explain than a beginning. A universe that starts at a boundary must account for the nature of that boundary. A universe that bounces must account for the transition. A no-boundary universe must account for the emergence of classical time. A past-eternal universe must account for infinite stability, controlled departure, entropy, perturbations, and compatibility with later observations. Each proposal removes one difficulty by accepting another. That balance is why no past eternal scenario is presently established as the actual history of the cosmos. The models demonstrate that classical singularity is not the only logical possibility, and some evade known beginning theorems by changing their underlying assumptions. But there is no observational evidence showing that the real universe spent an infinite past in an emergent state. The possibility remains open because the earliest regimes are not directly observed, and because fundamental physics is incomplete there. Yet the standard for replacing a beginning with eternity is severe. The model has to survive not merely for a long time, but without any hidden past boundary at all. If such a state existed, the hot Big Bang would become a transition in a universe with no first classical moment. But until a stable and testable mechanism earns observational support, past eternity remains not a conclusion, but one carefully defined way in which the beginning of time might disappear. If anything happened before the hot Big Bang, the most important scientific question is not whether such a history can be imagined, but whether it can leave evidence behind. Cosmology becomes testable only when competing descriptions of the early universe lead to different observable consequences: a bounce, an ekpyrotic contraction, an inflationary phase, a no-boundary quantum state, or a past eternal emergent universe may all produce mathematically consistent stories. But stories alone cannot decide which history nature followed. The present universe has to carry some surviving record of its earliest conditions. That record is difficult to read because most direct information from the deepest past has been erased, mixed, stretched, or transformed by later expansion. Yet several possible messengers remain. The cosmic microwave background is the clearest of them. It comes from a time long after any Planck scale regime, but its tiny temperature and polarization variations preserve information about primordial fluctuations that were already present before ordinary atoms formed. Those fluctuations are not random noise without structure. Their distribution across angular scales, their statistical relationships, and the way they appear in polarization can be compared with predictions from different models of the early universe. In many inflationary scenarios, quantum fluctuations are stretched to cosmic size during rapid expansion. After inflation ends, those fluctuations become variations in density and curvature that later seed galaxies and clusters. The resulting spectrum is expected to be nearly scale invariant, meaning that fluctuations have similar strength across a broad range of scales with a small, systematic departure from perfect equality. Observations support a primordial spectrum with this general character, which is one reason inflation remains influential. But near-scale invariance is not unique to inflation. Some contracting scenarios can also generate a similar pattern, especially ekpyrotic or matter bounce models designed to transform fluctuations during contraction and pass them through a bounce. The decisive information therefore lies not only in the broad shape of the spectrum, but in more subtle features that may differ between mechanisms. One such feature is non-Gaussianity. A Gaussian distribution is a particular statistical pattern in which the behavior of fluctuations is largely described by their average and variance. Many simple inflationary models predict primordial perturbations that are close to Gaussian, although more complicated inflationary dynamics can produce measurable departures. Bounce and cyclic scenarios can generate different forms or amplitudes of non-Gaussianity, depending on how perturbations evolve and interact before and during the transition. Detecting a distinctive pattern would not automatically prove one model, because different theories can sometimes imitate similar signatures, but it could eliminate broad classes of alternatives. Another potential messenger is primordial gravitational radiation. Gravitational waves are distortions of spacetime that can propagate across the universe, and quantum processes in the very early cosmos may have produced a background of them. Inflation can generate tensor fluctuations as spacetime rapidly expands, and their strength depends partly on the energy scale and dynamics of inflation. Some bouncing or ekpyrotic models predict a much weaker signal on the largest observable scales, while others produce spectra with different scale dependence. This makes primordial gravitational waves especially valuable in principle. A detected background with the right properties could constrain the physics of an era far earlier than the release of the cosmic microwave background. The difficulty is that the signal is expected to be faint and can be confused with foreground radiation from dust, galaxies, and later astrophysical sources. Cosmology therefore requires not only sensitivity, but confidence that the observed pattern truly belongs to the primordial universe. Polarization of the cosmic microwave background offers one route because certain curling patterns can be produced by gravitational waves. Measurements continue to improve, but there is not yet a confirmed primordial gravitational wave signal that selects one origin scenario over the others. The largest angular scales in the cosmic microwave background provide another possible window because they correspond to some of the largest physical wavelengths accessible in the observable universe. If the universe passed through a bounce or another pre-Big Bang phase, those longest modes might have been influenced differently from shorter ones. Some models predict suppression or enhancement of power on the largest scales, oscillatory features, or correlations that would not arise in the simplest inflationary history. Observed maps do contain unusual large-scale features, but caution is essential. Only a limited number of independent modes exist on scales comparable with the observable universe. So statistical uncertainty is unavoidable. A pattern can look suggestive simply because cosmology has only one sky to measure. This limitation is known as cosmic variance. It means that some of the most interesting possible relics of a pre-Big Bang era may also be among the hardest to distinguish from chance. The primordial density spectrum itself can carry further information. A smooth, nearly scale-invariant spectrum is not the only possibility. Brief interruptions in inflation, transitions in a contracting phase, sharp features in a field potential, or physics associated with a bounce can introduce localized changes in the amplitude of fluctuations. These could later appear as unusual patterns in the distribution of galaxies or in the cosmic microwave background. Again, the challenge is degeneracy. Different mechanisms can produce similar observational features. A bump or oscillation in the spectrum might arise from one form of inflation, from a pre-inflationary phase, or from a completely different interaction. To claim evidence for a universe before the Big Bang, a model would therefore need a combination of predictions that fit together in a way competing explanations cannot easily reproduce. Large-scale structure can extend this search beyond the microwave background. The positions of galaxies, the distribution of matter inferred through gravitational lensing, and the clustering of cosmic traces all preserve the later development of primordial fluctuations. Future surveys can map enormous volumes of the universe and test subtle departures from the simplest initial conditions. Because these observations sample many more modes than the microwave background alone, they can improve sensitivity to certain kinds of primordial non-Gaussianity and scale-dependent features. The difficulty is that billions of years of nonlinear gravitational evolution alter the original signal. Galaxies form through complex astrophysical processes. Matter collapses into halos, and environmental effects reshape what is observed. Extracting primordial information, therefore, requires careful modeling of everything that happened later. The farther a possible signature has traveled from the early universe, the more layers must be removed before its original meaning becomes clear. Gravitational waves may eventually provide a cleaner fossil record across a wider range of frequencies. Different early universe mechanisms can produce backgrounds with distinct spectral shapes. An inflationary background, a phase transition, cosmic defects, a bounce, or an ekpyrotic contraction could populate different frequency ranges and amplitudes. Space-based and ground-based observatories, as well as pulsar timing measurements, probe different parts of this gravitational spectrum. Most detectable gravitational wave backgrounds at present are expected to have astrophysical origins, such as populations of compact binaries, so the existence of a background alone would not establish primordial physics. The crucial task is identifying a component whose properties cannot be explained by known later sources. If such a component were found, it could offer access to epochs hidden from electromagnetic observation. Even then, the logic of confirmation would remain demanding. A successful pre-Big Bang theory must produce more than one attractive prediction after the data are already known. Ideally, it should make distinctive forecasts in advance and survive attempts to falsify them across independent observations. This requirement separates a flexible narrative from a predictive physical model. If every possible measurement can be accommodated by adjusting free parameters, the theory gains little evidential support. The strongest models are those that risk being wrong. They specify a range of possible primordial spectra, gravitational wave amplitude, statistical correlations, or large-scale anomalies, and can therefore be excluded if the universe does not display them. The search for a pre-Big Bang era is consequently a search for constraints as much as discoveries. Every tighter upper limit on primordial gravitational waves removes some models. Every improved measurement of non-Gaussianity narrows others. Every better map of large-scale structure tests how much room remains for departures from simple inflationary initial conditions. Science may approach the answer gradually, not through a single unmistakable relic, but by reducing the number of histories still compatible with all observations at once. It is possible that no surviving signal will ever uniquely reconstruct what happened beyond the earliest accessible boundary. Some quantum regimes may erase information too efficiently. Different theories may converge on nearly identical predictions for the later universe. Cosmic variance may permanently limit the largest scales. Yet even negative results have meaning. They tell cosmology which kinds of bounces, contractions, or exotic initial states are no longer plausible. The central standard remains unchanged. Any claim about what came before the Big Bang has to return to the sky. Theories can extend cosmic history into regions no telescope can directly see, but they become physical explanations only when some part of that hidden history changes what can be measured now. The earliest universe may be inaccessible as a place, but it is not automatically inaccessible as a cause. If a prior phase shaped primordial fluctuations, altered gravitational waves, or change the statistical structure of matter, then the present cosmos may still contain its imprint. The search is therefore not for a picture of an earlier universe. It is for a pattern that should not be here unless that earlier history really occurred. The question of when time began sounds simple only because ordinary experience makes time feel like a background that must always be there. Events occur within it. Clocks measure it. Memories point backward through it. And physical systems change as it passes. Cosmology unsettles that intuition because the earliest universe is also the regime in which the structure of space-time itself becomes uncertain. If the hot Big Bang was not an absolute beginning, then several very different possibilities remain. Time may extend through a bounce into an earlier contracting universe. It may continue without beginning through an emergent or past eternal phase. It may reach a quantum boundary at which ordinary temporal language loses its familiar meaning. Or time may not be fundamental at all, but something that appears only when a deeper physical system reaches the conditions required for a classical spacetime to emerge. These possibilities are not variations of one answer. They represent different ways of defining what an answer to the beginning question would even mean. In a bouncing cosmology, the issue is comparatively direct. A contracting branch lies on the other side of the transition, so the sequence of earlier and later can continue through a much longer history. The hot Big Bang then marks a change in cosmic behavior rather than the birth of time. The deepest problem shifts to whether the bounce itself can be described consistently by quantum gravity, and whether the earlier branch can be extended without encountering some still older boundary. A single bounce, therefore, does not guarantee an eternal past. It only shows how the familiar expanding phase could have a predecessor. A cyclic model extends this logic further by allowing multiple contractions and expansions. Yet repeated cycles do not automatically remove a beginning either. Entropy, stability, and the accumulated changes from one cycle to another may prevent the sequence from remaining identical or extending indefinitely. A model can contain many Big Bang-like transitions and still possess a deeper boundary. The existence of a past before the hot Big Bang is therefore not equivalent to the absence of all beginnings. Past eternal models make the stronger claim. In an emergent universe, the cosmos approaches an earlier state that can persist arbitrarily far into the past before expansion begins. If the model is genuinely geodesically complete and physically stable, there may be no first classical moment at all. Time simply extends backward without reaching an edge. But that answer creates its own questions. An infinite past must remain stable for an unlimited duration. It must avoid destructive perturbations, explain the thermodynamic arrow, and eventually produce the specific conditions that lead to the observed hot Big Bang universe. Eternity is not an explanation by itself. It is a property that a theory must earn by surviving both mathematics and observation. The no-boundary approach changes the problem more radically. Instead of asking how far classical time extends, it suggests that classical time may not be the correct language near the deepest quantum regime. The earliest geometry can be finite without ending at a conventional first temporal surface. There is no earlier classical universe waiting on the other side, but there may also be no singular first instant. The apparent beginning becomes a smooth quantum condition from which the familiar distinction between space and time emerges. Under such a description, asking what happened before can fail for a precise reason. The relation called before may not exist in the same form there. This is not a verbal trick. General relativity already teaches that time is not a universal background independent of physics. It is part of space-time geometry, affected by motion, gravity, and the distribution of energy. Quantum gravity may require an even deeper revision. If geometry itself has quantum degrees of freedom, then temporal intervals may not remain sharply defined at the smallest scales. A classical sequence of moments could be an approximate structure that appears only in suitable large-scale states. The possibility of emergent time takes this idea further. In some approaches to fundamental physics, the deepest description of a system can be formulated without a time variable that behaves like the one used in ordinary mechanics. Change can instead be encoded through relationships among physical degrees of freedom. One part of a system can function as a clock relative to another, and a sense of temporal evolution can emerge from correlations inside a larger quantum state. This does not mean that everyday time is unreal. Temperature is also an emergent quantity in the sense that an individual molecule does not possess a temperature by itself. Yet temperature becomes perfectly meaningful for large collections of particles. In a similar way, time could be physically real at the level of classical spacetime without being a fundamental ingredient of the deepest theory. If that picture is correct, then the beginning of time might resemble the emergence of a phase rather than the appearance of an object. There may be no earlier clock counting toward the moment when time switches on, because the clock concept belongs to the regime that emerges. This possibility is conceptually difficult because language is built around temporal order. Even phrases such as emerges from or becomes classical sound as though they describe a process occurring in a pre-existing time. A fundamental theory may have to express the relationship in a less intuitive way, using mathematical structure rather than a narrative sequence. That limitation is one reason current ideas about emergent time remain unsettled. They suggest ways to reconcile quantum theory with gravity, but there is no experimentally confirmed framework showing that cosmic time definitely arises from timeless underlying physics. The origin question, therefore, cannot yet be reduced to one preferred scenario. What can be said with confidence lies closer to observation. The universe has been expanding and cooling for approximately 13.8 billion years. The cosmic microwave background, primordial light elements, and the growth of large-scale structure strongly support a hot, dense early phase. Inflation provides a plausible earlier mechanism for preparing some of the conditions seen in that phase, but its exact physics and its own past boundary remain uncertain. Classical general relativity, extrapolated backward, encounters geodesic incompleteness and singular behavior, but those results do not provide a verified description of quantum gravity. Beyond that boundary lie proposals rather than established history. A bounce may replace the singularity. A cyclic sequence may embed the present expansion in repeated cosmic eras. An emergent universe may avoid a first moment. A no-boundary state may remove the need for an ordinary temporal edge. A deeper theory may reveal that time itself is secondary. None of these possibilities has yet acquired the observational support needed to become the accepted account of the beginning. This uncertainty has an important consequence for how the Big Bang should be understood. The phrase remains scientifically useful when it refers to the early hot, denser, expanding state and the evolution that follows. It becomes misleading when it is silently expanded into a claim that physics has demonstrated the absolute creation of space, matter, and time from nothing. Current cosmology has not demonstrated that. It has traced the universe backward to conditions of extraordinary temperature and density and identified where established descriptions become incomplete. That is already a remarkable achievement. But it is different from reaching the first fact that ever existed. The remaining problem sits at the intersection of cosmology, gravitation, quantum theory, and the nature of time itself. Future observations may narrow the possibilities. A primordial gravitational wave background could favor particular early universe mechanisms. More precise measurements of cosmic microwave background polarization and primordial statistics could constrain inflation, contraction, or bounce scenarios. Large-scale structure may preserve subtle signatures of initial conditions. At the same time, progress in quantum gravity could reveal whether spacetime remains continuous, undergoes a transition, emerges from more fundamental degrees of freedom, or possesses a genuine boundary. The answer may ultimately be observational, theoretical, or a combination of both. It may also turn out that certain aspects of the deepest past are permanently inaccessible, leaving several histories observationally indistinguishable. Even then, the distinction between what is established and what is conjectured will remain essential. The hot Big Bang is a supported chapter of cosmic history. The absolute beginning of time is not. The evidence reaches back to a universe that was once far hotter, denser, and smoother than the one that exists now. But the final step from that history to an ultimate origin has not been taken. What lies beyond may be another era, a quantum transition, an eternal past, or a level of physics in which time is no longer fundamental. For now, the most precise conclusion is also the most open one. The Big Bang marks the beginning of the cosmic history that can be reconstructed with great confidence. But whether it marks the beginning of time itself remains one of the deepest unresolved questions in modern physics. Across the long history of cosmology, the Big Bang remains one of the strongest conclusions science has reached about the early universe. Yet its meaning is quieter and more precise than the familiar image of a sudden creation. The evidence points toward a cosmos that was once hotter, denser, smoother, and more tightly connected than the universe that exists now. From that state came expanding space, cooling radiation, the first nuclei, the first atoms, and eventually the structures that filled the darkness with stars and galaxies. But when that history is traced toward its deepest limit, certainty begins to thin. Classical relativity points toward a singular boundary. Quantum gravity suggests that the boundary may not be the final description. Inflation may place another phase before the hot Big Bang. A bounce may connect expansion to contraction. Cyclic models may place the present universe within a longer sequence, and no boundary state may replace the first instant with a different kind of geometry, while an emergent universe may extend time indefinitely into the past. There is even the possibility that time itself belongs only to the large-scale world, arising from deeper physics, in much the same way that other collective properties emerge from simpler ingredients. None of these possibilities has yet become the established answer. They remain constrained by mathematics, by observation, and by the requirement that any deeper history must eventually produce the universe already known so well. For now, the earliest cosmos remains a boundary between confidence and possibility. Science can follow the evidence remarkably far. And then, at the edge where space-time itself becomes uncertain, the story opens rather than closes. The Big Bang may still be the beginning of the universe as it is known, without being the beginning of time itself.